let me greet you and all the participants with a good morning from Rio de Janeiro. It's about 8:30 here. Although we had a lot of rain during November, today it's a sunny day and the temperature is around 25 centigrades. Before I start, I would like to say that it's a great honor for me to make this presentation, and I would like especially to thank the conference organizers for the invitation. In particular, Professor Mohamed Garoun, Professor Najim Alahous, Dr. Zaid Romani, and Professor Youssef Vaz. I also congratulate them for the very nice and extremely well organized conference amid the pandemic. And this work, it's actually a very specific topic, and, but it's a collaboration with Julien, Bergera, and Thibaut, Colinartb, and Bruna Loiolac. Julien is from Université de La Rochelle, Thibaut from Université de Bretagne Sud, and Bruna Loiolac, she's a faculty member of the Military Institute of Engineering in Brazil. Let me tell you up front that my name is the last one in the list of authors, not because I was the head of this research, but really because I was the one that who did the list of work. This work has been published in the Journal of Wood Science and Technology. It has just come out. And this is the summary of my presentation. I'm going to make a brief introduction, the motivation and objective, talk about the experiment, the mathematical models, the approximate Bayesian computation algorithm for simultaneous model selection, model calibration, results and discussions, and then the conclusions. So, human curiosity about natural phenomena has always played a fundamental role for the advancement of science. In fact, the search for the truth, what is called the truth, has passed through the analysis of empirical evidences. And as natural phenomena were better comprehended, attempts have been made for the theoretical model. And here, quote Fourier, who wrote in his treatise that the profound study of nature is the most fruitful source for mathematical discoveries. Modeling of natural phenomena generally involves conservation laws and constitutive equations based on empirical results. Moreover, models are based on hypotheses, which directly affect the mathematical formulation of the problem in terms of the number of dimensions, time dependence, scales, linearity, model parameters, etc. In general, more complex models are usually proposed as knowledge is built up with the advancement of science. But commonly, these models are over-parameterized and not necessarily more accurate than simpler ones. Thus, the principle of parsimony must be pursued to obtain simple models with a small number of parameters which accurately represent the phenomena under analysis. So besides situations where the models can be written based on conservation principles and constitutive equations, there are many others that strongly rely on empirical evidences, including experimental data or a priori knowledge about, like a personal own experience. For example, such is usually the case in biology or economics. And more recently, data-driven models based on artificial intelligence tools have been gaining great interest of the scientific community, but such meta-models will not be considered here. Parameters appear in any mathematical model of natural phenomena, from the simplest to the most complex ones. The estimation of parameters or functions appearing in mathematical formulations of problems in nature by using measurements of some response of the system and the calculated corresponding dependent variable of the model is an inverse problem. In this work, we consider the solution of inverse problems within the Bayesian framework of statistics, where credit is also given to previous beliefs about the unknowns, in addition to the information provided by the measured data. Such previous information can even be qualitative, but needs to be represented in terms of a probability distribution function. And these prior distributions, they promote regularization of the solution of the inverse problem, but unfortunately, they induce bias. The term Bayesian is commonly used to refer to techniques for the solution of inverse problems that fall within the framework of statistics developed by the Presbyterian minister, Thomas Bayes. Such framework was actually established after Bayes' death, when his friend Richard Price, in this paper, he published Bayes' results. On the other hand, it's attributed to Laplace the mathematical formulation that is known today as Bayes' theorem. The solution of inverse problems within the Bayesian framework of statistics relies on inference of the posterior distribution of the parameters. In this context, Bayes' theorem relates the posterior distribution, which is the conditional probability of the parameters P given the measurements Y, to the prior distribution and to the likelihood. The prior distribution is the statistical model of the information available about the parameters before the measurements are taken, while the likelihood is the statistical model of the measurement errors, which also represents the conditional probability of the measurements Y given the parameters P. The distribution appearing in the denominator of Bayes' theorem is called evidence, and it's actually a normalizing constant for the posterior. The computation of this of the evidence is difficult, so that many times Bayes' theorem is simply stated as the posterior being proportional to the prior multiplied by the likelihood. There are many situations in practice where the likelihood is not exactly known and cannot be approximated in terms of analytical distributions. There might also be situations in which the calculation of the actual likelihood demands large computational times and resources, thus requiring model reduction or data compression. While the approximation error model approach, which was developed by Jari Kaipi and his colleagues, can be quite effective when a Gaussian distribution can be used for the total errors. And by total errors, I mean the measurement and modeling errors. This Gaussian model cannot be arbitrarily used in general. It's also important to note that data compression schemes like the ones quite popular nowadays, based on artificial intelligence, they might not result on an analytical likelihood. So the so-called approximation Bayesian computation, it can deal with measurement and total errors that may not be appropriately modeled in terms of an analytical distribution, or if the computation of the likelihood function is very time-consuming. We now come to the motivation for this work, which is related to the use of green materials for construction. Within the environmental context, bio-based materials have been increasingly used in building constructions due to their reduced ecological footprint and their thermal performance. Besides that, the properties of wood-based materials have a good reproducibility due to their industrial production. However, several recent studies pointed out the importance of accurately modeling the phenomena of water sorption in such materials to predict the phenomena of heat and mass transfer and to assess moisture disorders like mold growth. So the sorption curve is an essential feature for the modeling of heat and mass transfer in porous building materials. Several models have been proposed in the literature to represent the amount of moisture content in the material according to the water activity. And these models are based on analytical expressions and few parameters that need to be estimated by inverse analysis. Therefore, we come to the objective of this work, which was to select among 8 competing models, the one most appropriate to represent the measurements of water content in a wood fiber construction material during controlled sorption experiments. The model parameters were estimated simultaneously with the model selection by applying the ABC algorithm of Tonetal, which can be found in these references below. Although it can be claimed that the measurement errors in this work could be analytically modeled in order to be used for model selection and calibration, the authors have successfully used this algorithm for many applications, and then we have decided to go ahead and also use it for this work. About the experiment, this sample material was a wood fiber thermal insulator. It's commercially available under this name of PavaFlex Comfort from this supplier. It has a density of 50 kilograms per cubic meter and a thermal conductivity of 0.038 watt per meter Kelvin. Due to its low thermal conductivity, this bio-based material has been used as a building envelope, but it presents a strong hygroscopic behavior. So the sorption curves sorption curves were measured with 5 samples of this material by using a dynamic vapor sorption equipment, where the sample was placed in a chamber with controlled conditions of temperature and water activity. And during the experiment, the mass of the sample was continuously measured. And before the experiment, each sample was dried for 24 hours. The dry mass of the samples varied from 10.8 milligrams to 28.2 milligrams. Each sample was exposed to increasing water activity from 0.05 to 0.95 at a constant temperature of 23 centigrades. And the sample was maintained at each of these water activity levels until the moisture content in the sample reached equilibrium. The sample mass increased rate was carefully examined before moving to another activity level as a stopping criterion at each water activity step. This slide shows the equipment that was used for the experiment, as well as the variation of the sample's moisture content with the water activity. And for the 5 samples, and we can see that there is a good repeatability of the experiment, as we can even see with these zooms of the 5 curves, except for the very large water activity. The following 8 mathematical models were examined in this study. Actually, the model, they provide the moisture content U as a function F of the water activity A. And each model, it contains N parameters, and the parameters are represented by those P variables. And the domain of the water activity was limited to this interval between 0.05 and 0.95, because some of the models are not valid for A equals 0 or for A equal 1. So these are the mathematical models. This Bruna or Emmett-Teller model, it's given in this form. It has 2 parameters. The Guggenheim-Anderson-de Boers model has 3 parameters. Now the thermodynamic model, it also has 3 parameters, and it's given by this expression. The empirical Oswin model, then it has 2 parameters. The Fred-Long-Zing model, it has 4 parameters. the Van Genoosten's model, 3 parameters, and one additional parameter based on the literature was this one by Smith with 2 parameters. But this, we also proposed a new model in this work, and this was inspired by the shape of the sorption isotherm and its derivative, as compared to the tangent function. So the algorithm of Ton et al. For model selection, for simultaneous model selection and model calibration, I mean the estimation of the model parameters is presented in this slide. And the objective here is to obtain the combined posterior distribution of the model and its parameters with the given measure data. In this algorithm, at the first iteration, a model is initially selected from its prior, and then a sample for the parameters of this model is obtained from its prior distribution, as illustrated here. This process of selecting the model and the sampling the parameters is repeated until a pre-specified number of samples are accepted. And a user-selected distance function between measurements and estimated moisture content is used as the acceptance criterion instead of the likelihood. And this is done with a specified tolerance epsilon. And this tolerance epsilon, it varies at each population. The set of accepted, and by population, I mean the set of accepted samples. So new samples are generated by sampling the model from its prior, and the parameters from their estimated distribution at the previous population. This process is repeated until the tolerance for the last population is satisfied. And as I mentioned, the tolerances are usually, they are reduced as the populations advance. They are usually set large for the first populations. And this is we do this in order to avoid lack of convergence when the sample is dominated by the prior. And as the information provided by the measurement becomes more and more significant as the populations advance, and then a large number of cells is selected for the correct model, and the samples for the parameters better reflect the real posterior distribution. Now we come to results and discussions. And before trying to estimate the parameters, we addressed the questions related to the identifiability for each model that was considered in the analysis. Since all models are simple and analytic, the structure of global identifiability was verified, thus shown for all models, thus specifying that a specific sorption curve could only be obtained with one single set of parameters, and this was verified for each model, as I mentioned. The sensitivity coefficients were also examined for each parameters, and the sensitivity coefficients are given by the first derivative of the model response. In this case, the moisture content. With respect to each parameter, it's represented by the variable theta. And as an example, we present in this slide the sensitivity coefficients for the parameters of this GAB model. And since the parameter estimation problem is nonlinear, the analysis of the sensitivity coefficient is local. So these two figures, they show the sensitivity coefficients computed with two different sets of the model parameters. For both cases, we note that the sensitivity coefficients are not linearly dependent. And also, the magnitude of the sensitivity coefficient with respect to the parameter P3 is much smaller than those for the other parameters. Therefore, the moisture content for this model, or predicted with this model, is very little affected by this parameter. And unfortunately, its estimation with high accuracy is difficult in this case. The global sensitivity index that is obtained by the integration of the square of the sensitivity coefficient in the activity and parameter domains. It was also used to assess the sensitivity of the model of the moisture content with respect to each model of each parameter of each model. I'm sorry, as shown in this table. And we can, this global sensitivity index is actually a relative quantity. And we can see that it confirms the results that we have seen by the analysis of the sensitivity coefficients, which shows that the GAP model is very little affected by this parameter P3. Actually, this table shows that only these Smith's, which is the SM model, and the model proposed in this work, which is this MADS model, they are the only two that all parameters are equally, more or less equally affect the measured quantities. So for the implementation of the ABC algorithm of Ton et al., the distance function was taken as the Euclidean distance between estimated and measured moisture content. As I mentioned, the tolerance aimed at as the populations evolved, and we tried to satisfy Morozov's discrepancy principle at the final population. This variation of the tolerance as the populations evolved, it was selected by numerical experiments. And this was also the case for the number of populations, which was selected as 22, and also the number of particles, which was selected as 4,000. The perturbation kernel that is used to explore the parameter space at each population, it was chosen as a random walk move with an uniform distribution. And a maximum perturbation of 1% of the maximum parameter value was used for this kernel. But as I'm going to show in the presentation, that the results, they were not affected by this kernel. All models, they were assumed as equally probable, and the uniform priors were also given for all parameters. And the ranges for these priors, they were also obtained from numerical experiments and from literature values, so that the resultant moisture curves obtained from the models, they could encompass all the experimental results. So these are the uniform priors, and you see that for some of them, they actually are not very much informative, and they actually encompass a large variation of they include a large variation of the parameters. Okay, so this figure, it shows how the tolerance was varied as the populations evolved. These are the number of populations, and while this figure on the right, it shows the acceptance rate at each population. Okay, so we see that the acceptance rate, it decreases with the population, and this is because the tolerances were reduced. And also, we note here that the acceptance rate is strongly dependent on the size of the kernel that was used to search the parameter space. When this kernel was increased from 1% to 10%, we see a sharp decrease in the number of accepted in the acceptance rate. Because it's more difficult to improve the agreement of simulated and measured moisture contents with candidates generated with such a large kernel. This figure shows the model selection through the 22 populations. And this was for the kernel of 1%. And initially here, the 8 models, they have the same number of particles. But in the until population 4, there was no strong selection among these 8 models. However, at population 5, Smith's model was then less selected, since it did not succeed in representing the moisture for high water activity. And that at population 5, no particle satisfied this distance test, the distance test for this model with the candidate parameters. Thus, after population 4, Smith's model was no longer selected. And at population 9, it can be noticed that only 3 models were still competing. The model proposed in this work, this MADS model, the FX model, and also the GAB model. At the final population, only the MADS model satisfied the distance test for the lowest tolerance. Although this was the only model selected from population 20 onwards, the last 3 populations, they were needed to correct the calibration of this model to better select to better estimate the parameters for this model. We also note that in this figure that the results, they were not significantly affected by changing the kernel to 10%. And at the final population, still the model proposed in this work was the only one accepted. It's also interesting to note that the dispersion of the samples of the parameters as the population evolved. So in this figure here, we can see this shows the increase in the population number. These are the parameters, and each dot here represents one of the samples of the parameters at each population. Okay, so as the populations advanced and the model better reflects the experimental data, so the variation of the parameters, it decreases. This can also be seen by this figure here, which shows the standard deviation of the samples of the parameters. And at the final iteration, we can actually obtain these approximate marginal posterior distributions for the 2 parameters of the MADS model, which in fact they exhibit small variances. The accuracy of the selected model with the correspondent estimated parameters, it can also be assessed by comparing the model predictions with the measured data. As shown in this figure, in blue we have the experimental measurements, and in red here we have the simulation under uncertainty on the parameters. I mean that the parameters, they were sampled from their posterior distributions, from their simulated posterior distribution. And actually the moisture content predicted with this model and with the uncertainty in the parameters, they exhibit a small dispersion. And they also exhibit a good agreement with the experimental data, even for large water activities. Now some conclusions, and a new model was proposed for the sorption curve of a thermal insulation material made of wood fibers. And this model was inspired by the shape of the sorption curve in comparison to the tangent function and also its derivative. The ABC algorithm of Ton et al., it was used for simultaneous model selection and model calibration by considering 8 competing models. And the proposed model was the one selected. And actually, the approximate posterior distribution of the estimated parameters exhibited small variances. Similarly, the moisture content simulated with the selected model and with the approximate posterior distribution of the parameters had small variances. The CPU times, they were about 50 minutes for the kernel of 1% and 30 minutes for the kernel of 10%. The difference in computational time is due to the reduced acceptance rate for the kernel of 10%. But still, it's a small computational time, and these were obtained with a MATLAB code running in a computer with an i7 CPU and 30 gigabyte of RAM. So this basically concludes my presentation, but let me make was the opportunity to make an announcement. Actually, this announcement was made about the same date last year in Agadir during Zurich 19. I'm organizing this 8th International Symposium on computational heat and mass transfer. The symposium belongs to the series of conferences of the International Center for Heat and Mass Transfer. Unfortunately, we had to postpone the conference because of the pandemic. Had to take this decision in the worst occasion of the pandemic here in Brazil. The conference is going to be held next year in hybrid format with in-person and online presentations. And the one-page abstract is due December 18th. Okay. So finally, again, thank you very much, the organizers, Professor Gahum, Professor Lahus, Professor Zaz, Dr. Romani. Very great pleasure to be here. And I'd also like to acknowledge the support provided by agencies of the Brazilian government, and also the French colleagues want to acknowledge the Junior Chair Research Program from the University of Savoie-Mont Blanc, in collaboration with the French Atomic and Alternative Energy Center and the Scientific and Technical Center for Buildings. So this concludes my presentation, and thank you very much for your attention.